So today we'll continue from the previous lecture of semester 4 physics honors related to operators. Now today we'll start from eigenfunction and eigenvalues. Now we'll just assume an operator A cap, okay, which will operate on a function psi as a function of x. Okay, now when we'll operate on this, the operator on this function psi x, it's a well-defined function, we'll get something like beta into psi as a function of x. Here beta will be the eigenvalue and this one will be the eigenfunction. So basically, to understand in a very simple way, what we can say that if an operator operates on a certain function, we'll get the same function multiplied by some kind of a constant. So this is the basic equation, the simple way to understand eigenfunction, eigenvalues. We just take an example, very simple example. Say for example, we'll take dy dx as an operator A, okay, and psi x as e to the power minus 2x, say for example like this. Now it's a well defined function, so we'll operate, okay, on psi x. We will get dy dx to the power minus 2x, which will be minus 2 into to the power minus 2x, which is equal to minus 2 into psi as a function of x. So what we can say is that we just see that after operating with the operator a cap, we'll get the same function multiplied by the constant term, which is the eigenvalue in this case, and this is an eigenfunction. Now the same operator cannot act like a the same operator cannot act like a the eigenfunction. It cannot be used for same eigenfunction, like say suppose the same operator we are using for a function cos 2x, which is here we have taken again psi x is equal to cos 2x. So we'll just write d by dx cos 2x, we'll get minus 2 sin 2x, where minus 2, this sin 2x further is not cos 2x, it's not equal to cos 2x. So here what we can say is that this cannot be an eigenfunction for d by dx. So for operator a cap, okay, cos 2x is not an eigenfunction. It may be an eigenfunction for d square by dx square, but in this particular case this is not an eigenfunction. So that is how you have to move ahead. Okay, now again further what we will discuss is about the linear momentum operator. So what is the linear momentum operator? So we will talk about linear momentum operator. So when I say linear momentum operator, we denote by minus I h cross del by del x. Okay, so this is the linear momentum operator. Now how to derive this linear momentum operator? We'll again consider a well-defined function psi as a function of x comma t equal to, say, psi naught into e to the power minus I by h cross into, okay, et minus, say, p into x. So we'll consider the wave to be moving along x direction. So further what we'll write is psi naught minus I by h cross et minus p subscript x into x. Okay, so if we'll differentiate with respect to x, so we'll get something like this: del psi by del x equal to I px by h cross, I px by h cross minus I by h cross et minus p subscript x into x. So this will be finally equal to I p x by h cross into psi. Okay, so here we missed out psi naught. Okay, so now this will be equal to h cross by I del psi by del x equal to px psi or p subscript x into psi equal to minus I by h cross del psi by del x. So from here we can just assume p operator p subscript x is equal to minus I h cross del by del x. So this is the momentum operator, and it could be uses the form of a component also. In the place of x, we'll just write p subscript y operator is equal to minus I h cross del by del y, or pz is equal to minus I h cross del by del z, as we wish. Further moving ahead, we'll just talk about the energy operator. Okay, in this case we'll just talk about the Hamiltonian, so that is time dependent form. So again we'll take the same function psi as a function of x comma t is equal to psi naught e to the power minus I by h cross et minus px. So again differentiating with respect to t, we'll get del psi by del t equal to minus I by h cross e psi, or e psi is equal to I h cross del psi by del t. So here, from here, what we can say that the energy operator is given by E cap is equal to I h cross del by del t. So this is about the energy operator. Further, what we can do is that we can consider the linear or rather angular momentum operator. So talking about the angular momentum operator, it's like let's write about the angular momentum operator. Angular momentum operator. So talking about the angular momentum operator, we'll just consider angular momentum L is equal to r cross p. Okay, so this is the basic definition for the angular momentum. So in the place of r we can substitute it's in Cartesian form. Okay, Cartesian form. So this will be given by I, j, k, x, y, z, and here we write px, py, pz. Okay, we have assumed over here r to be xi plus yj plus zk, and p is equal to pxi plus pyj plus pz. Okay. So this is the cross product basically. Now taking the component wise, so after expanding this determinant, we get L subscript x is equal to y pz minus z py. Similarly, Ly is equal to z p subscript x minus x p subscript z, and L subscript z is equal to x p subscript y minus y p subscript x. Converting it into operator form. Okay, I'll just discuss the first one and the rest of you can do it of your own. Minus z operator py. So the operator of the position is again the position vector itself into p z cap. So in the place of this we'll write minus I h cross del by del z, minus z cap is z, and py is minus I h cross del by del y. So we'll get minus I h cross, okay, and here we'll have y del by del z minus z del by del y. So similarly we can write Ly is equal to minus I h cross, okay, z del by del x minus x del by del z. You can find out this one of your own, and Lz cap is equal to minus I h cross, okay, that is x del by del y minus y del by del x. Moving ahead further, you can just find out the the same thing in the spherical polar coordinate. Spherical polar coordinate, that is r, theta and phi. What we have to do is that we'll just have to assume x to be x equal to r sine theta cos phi, then x cos theta r cos x is equal to r sin theta cos phi. We'll write y is equal to r sin theta sin phi and z is equal to r cos theta. Again moving ahead, we'll write r is equal to, we'll write r equal to under root x square plus y square plus z square from the same, and cos theta will be equal to, from the last equation, cos theta is equal to x by z by r, rather z by r, and tan phi is equal to y by x. What we'll do is that we'll just try to find out, okay, del y del x, del y del y, and del y del z in terms of r, theta and phi. So what we'll do is that we'll consider a function u, or say a is equal to a as a function of r comma theta comma phi. Now del a by del x equal to del a by del r into del r by del x. We're using the chain rule of partial differentiation over here. Again, del a by del theta into del theta by del x plus del a by del phi into del phi by del x. Now what we'll do is that we'll use these three expressions, okay, to find the value of del r by del x, then del a by del theta, and del a by del phi. So we'll just see how we can find out like that. Now differentiating this one, okay, with respect to x. So if we differentiate r under root x square plus y square plus z square with respect to it, we'll have del r by del x equal to x by r. Substituting the value of x over here, we have x is equal to r sin theta cos phi. So r sin theta cos phi by r will give you sin theta cos phi. So this is the value of del r by del x. Okay, then what we'll do is that we'll differentiate this one, the cos theta by zr, with respect to del x again. So differentiating this one, cos theta z by r with respect to x, will get minus sin theta del theta by del x equal to minus z by r square del r by del x. Okay, so ultimately after solving this, we'll get del theta by del x equal to cos theta cos phi by r square sin theta. Okay. Further differentiating this last one, tan phi is equal to y by x, again with respect to x, we'll get del phi by del x equal to minus sin phi by r sin theta. So we'll get this del phi by del x, then del theta by del x, and del r by del x. We'll do one thing, we'll just substitute these three values, okay, in the chain relation which we have assumed over here. Okay, so ultimately we can find out from there del a by del x by substituting this value, that is del a by del, we'll substitute the value del a by del r, or we have assumed over here, whatever we have assumed over here, we have find out the relation, okay, and we'll substitute over there. Substituting the value, we'll get this relation, del a by del r equal to sin theta cos phi del a by del r plus cos theta cos phi by r, again del a by del theta, minus sin phi by r sin theta, okay, into del a by del phi. So this is what you will get, okay, and then from here you can find out del by del x. So ultimately after solving this thing, we'll get the expression of the spherical polar coordinate, the orbital angular momentum in terms of a spherical polar coordinate. Similarly, just what we have done over here, we'll just find out del by del x. Okay. Similarly, you'll find out del by del y and del by del z, substituting and using the same chain relation, and substituting this in this particular expression. Okay. We'll get the answer for that. So this is how we'll get the expression of this angular momentum in the spherical polar coordinate. Thank you.